In section 6.7, we're going to look at the other big integration technique in this course, integration by parts. As U substitution or substitution was going back through the chain rule of derivatives, integration by parts is going to be going backwards through the product rule of derivatives, although it's not going to be as obvious that's what we're going to be doing. To show that this is related to the product rule, we're going to first think about the product rule, and we're going to do some algebra and some integration to show that this formula we're going to use in a little bit is heavily related to the product rule. So first, let's introduce the product rule again. If we have two functions multiplied together, in this first case, f times g, and we take the derivative of the first times the second plus the first times the derivative of the second, f prime g plus fg prime. We're going to rewrite that slightly in the second line to not have f and g, but we're going to use the functions u and v. The reason we're doing this is because this is going to be consistent with what many texts and many resources use for integration by parts. The reason that u and v are used is because u is a common variable to represent a substitution, and we are going to be doing a substitution here in a similar fashion as u substitution. However, what we're really going to use for the product rule is this third line, and that is just rewriting the second line, but with the ddx Leibniz notation rather than the prime notation. So when we say uv prime, that means the derivative of u times v. And another way to write that is ddx of u times v, but we're just going to bring that uv into the numerator and write it as duv dx in the denominator. Similarly, u prime we can rewrite as du dx, and v prime we can rewrite as dv dx. Writing it in this notation is going to allow us to see how this integration by parts formula comes about. So again, we are going to use this last iteration of the product rule, and we're going to take the integral of both sides with respect to x. So I'm going to write that down here. We're going to have the integral of the left-hand side is going to be equal to the integral of the right-hand side. So the left-hand side here is this duv dx, and the right-hand side is du dx v plus u dv dx. And the first thing that we need to look at is that when I take the integral of the derivative, those things are going to cancel out. The integral allows us to take the antiderivative, and if we take the antiderivative of the derivative, those are inverse operations, and they're just going to cancel out, and we're going to be left with just u times v. On the right-hand side, we are going to first rewrite this as the integral of du dx v times dx plus the integral of u dv dx times dx. We're just going to break that integral up by addition. And when we do that, we can do some algebra here and cancel out these dx's on the top and the bottom. The reason we didn't do that on the left-hand side is because we have this nice rule that we can cancel out the derivative. But since we're multiplying things here, we can't easily do that. Finally, we can rewrite this as u times v on the left is going to be equal to the integral of, we're going to write this as v du plus the integral of u dv. And finally, we're going to get our integration by parts formula by doing a little subtraction here, and we're going to write the integral of u dv is going to be equal to uv minus the integral of v du. That is just subtracting that big integral from both sides. And this is our integration by parts formula we're going to look at on the next page. So again, we start with the product rule of derivatives. We take the integral of both sides and do some algebra, And we're left with this equation that is true that's going to allow us to do some integrals in a nicer way. So again, this integration by parts formula is the integral of u dv is equal to uv minus the integral of v du. So when we're going to be using this formula and using this technique, we're going to be looking at an integral that has the multiplication of two functions. And our first goal is going to be identifying or calling one of them u and one of them dv. Again, we have two functions here. We have a u and we have a dv. We're going to multiply them together, or they're going to be multiplied together, and we're going to try to identify which one is which. Now we're going to use this formula to rewrite this integral on the left-hand side. We're going to rewrite it as this subtraction, and we're going to be left with an integral on the right-hand side that will be easier to do. And that's the goal of every integration technique, is to simplify the integral into an integral that is easier to do. The difficult part of integration by parts is identifying which function should be u and which one should be dv. After you get to that point, it's just going to be kind of a plug and chug formula, which takes some practice to get used to, but there's not a whole lot of thinking that we have to do past that first moment. However, it can be difficult to decide which one is which, or deciding that integration by parts works in the first place. Note that in order to use this formula, we also are going to need to find du, which we're going to call the derivative of u, just as dv is the derivative of v, and v, which is the antiderivative of dv, just the original function v. So we're going to often look at these four functions written like this. We're going to have u and dv be our functions from our integral, and we are going to take the derivative of u to find du, and we're going to take the antiderivative of dv to find v. And after doing that, our formula, we are going to have u times v, that's going to be those two functions multiplied together, minus the integral of v du, which is going to be these two functions multiplied together. And as long as this integral is easier to do, then we've done our job. So this integral should be easier to take care of. If it is not easier to do, then this technique may not be helping us at all. And we'll see some examples here of what we're talking about. So the first example is a very common example for integration by parts, and that is x times e to the x. It may be useful to think about what other techniques we have. So we have some straightforward antiderivatives, but this doesn't follow any of these rules. We know what the antiderivative of x is. We know what the antiderivative of e to the x is, but we can't do that with the multiplication together. We may then think about a substitution. There is function composition here, but that function composition would only give us the possibility of having u equals x, and that's not going to help us out for u substitution. So we are left with this possibility of doing integration by parts. We have two functions here. We have x, and we have e to the x, and we're going to have this dx come along the way. We'll see how that's going to work. So we're going to break up this entire integrand to deal with the x, e to the x, and dx. I'm going to tell you right now that the choice of u being x and dv being e to the x times dx is going to be the correct choice. So we're breaking up this integral to be x times e to the x dx. The reason for that is because the next thing we have to do is take the derivative here. And when I take the derivative of x, I get a much easier function to deal with, that being just 1. I also need to take the antiderivative here. and that's going to be the antiderivative of e to the x dx, which is just going to be e to the x. And usually antiderivatives are going to give us more complicated functions, but in this case, we just get the same function back, and that's the biggest reason why this works. Now let's see the actual application of the integration by parts formula. Our original integral is the integral of x e to the x dx. That's our original integral. This is going to be equal to u times v, that is x times e to the x, and we are going to subtract off du, or the integral of v times du. And note that I should have a dx here because I took the derivative. That's where that dx is going to come from. E to the x. And this integral, this is a doable, straightforward integral. So our answer here is going to be x e to the x minus the integral of e to the x. We don't have to think about the 1, it just goes away. And that's going to be x e to the x minus just e to the x plus the constant c at the end. So again, I sort of told you what the choice is going to be in this problem. We'll look in the next page what are some good choices. But the reason that it worked is because the derivative of u became an easier function to deal with, and the antiderivative of dv didn't make the function much more complicated, which made that second integral easier to do, and that's the whole goal. So let's look at some common applications of integration by parts, common things that we should look for. When we have a polynomial times an exponential function, note that's exactly what we just dealt with. We have something like x times e to the x dx. We let u equal the polynomial function, in that case the x, and we let dv equal that exponential function. Another thing that we could look for is a polynomial times a trig function. That might be something like, we'll do something a little more complicated, like x squared plus 1 times sine of x dx. In this case, integration by parts would work by letting u equal the polynomial x squared plus 1 and dv be that trig function, either a sine or cosine. Then on top of that, we have, if we have just the integral of a logarithm or a polynomial times a logarithm, then we can also do integration by parts. So that might look something like x times natural log of x dx. In this case, we let u equal the logarithm. We'll see an example of this on the next page. And let dv equal the polynomial. That's kind of backwards and maybe what you would originally think, and we're going to see why that works on the next page. A much less common but still applicable way of doing integration by parts is seeing a polynomial times a square root function, or something like a square root function. This will also work by letting u equal the polynomial and dv the square root. I want to make it very clear that this is not an exhaustive list, and integration by parts can be used in a lot of other different scenarios. This is just going to be a list that represents the usual suspects that we're going to take care of in this class. And note that we could spend more time on integration by parts and look at many other examples that work, including inverse trig functions are good for integration by parts, as well as a lot of other unique scenarios. Now let's look at a definite integral and an application of this logarithm thing we were talking about on the previous page. Now what's interesting about this problem, we're going to ignore the definite integral part for right now. We'll just look at this natural log of x dx. And that is, what are our two functions that we're multiplying together? And in this case, we only have two options. That is the natural log and just the dx. And just having the function dx may seem scary, but we'll see what's going to happen there. Let's look at our wrong choice of u and dv first. Also note that we could write this as the integral from 1 to e of natural log of x times 1 times dx. That's going to be important here. So the wrong choice of u and dv would be letting dv be the natural log of x times dx and letting u be just that function 1. Let's see what happens here if we did this. We would have the derivative of 1. Remember, we've taken the derivative here. The derivative of 1 is 0. We're going to have that dx come along for the ride, and that is a very nice thing. Having 0 is the easiest function we could deal with, so that's good. Now let's try to take the antiderivative here, and we run into a huge issue, and that's because in order to do this, we have to find the antiderivative of natural log of dx. And this is our original problem. If I knew what this was, then I could just finish the problem at this point, but I can't do it. This is a big old question mark, and that's not going to work here. Let's instead flip it, and let's let natural log of x be our u, and we're going to let dv be our 1 dx. Here, the derivative is going to be 1 over x times the dx. We've made that function easier to deal with. Natural log is not an easy function to deal with. 1 over x is still maybe difficult, but much easier to deal with. And then I'm also going to take the antiderivative here. The antiderivative of 1 dx is just going to be equal to x. And in that case, we've made the function more difficult to deal with, but we're going to see how that works. So putting this all together, we have the integral from 1 to e of natural log of x dx is going to be equal to u times v. That's going to be on this diagonal. That's going to be this x natural log of x. And then we're going to have that bottom line in the integral. So minus the integral of 1 over x times x dx. And a few things to note. One is we have to think about the definite integral now. And to deal with the definite integral, we are going to evaluate this first chunk from 1 to e, and this integral is still going to be from 1 to e. The second thing to notice is that in that second integral, that may look complicated, but these x's cancel out, and we are left with the integral x natural log of x from 1 to e minus the integral from 1 to e of 1 dx. And that is an integral that we actually just did earlier in this problem. I'm going to go to the next page to finish this off. So right now we have that this integral is equal to x natural log of x evaluated from 1 to e minus the integral from 1 to e of 1 dx. And the quick note I have here is that when evaluating a definite integral with integration by parts, we could just wait until the very end after taking this second antiderivative here, this second integral, and then plug in the bounds as a whole. I think that's an easier thing to do rather than take care of each part separately. But you could take care of this evaluation from 1 to e and do the evaluation of 1. But we're going to see here that if I do this antiderivative, I'm going to be left with x natural log of x. The antiderivative of 1 is just x. And I'm going to evaluate the whole thing from 1 to e. So doing this, we're going to have e times natural log of e minus e minus 1 natural log of 1 minus 1. We have that natural log of e is equal to 1. We have that natural log of 1 is equal to 0. So we could simplify this. This is going to be e minus 0 minus 1. E minus e is 0. This is going to give us just a positive 1 as a simplified answer. Last note here is if you don't want to wait till the second derivative, then you would have to write this as e natural log of e minus 1 natural log of 1, and then minus the integral from 1 to e 1 dx. You have to do those kind of things separate. I think that just takes more work. We're going to look at some more practice problems with integration by parts in the next video.